Good morning, everyone. I'm Mike Fagan. I'm the Chief Big Data Architect at Comcast for Enterprise Hadoop. And I'm here joined with Dushyant Vidi and to talk about our Hadoop Query Performance Smackdown that we conducted a few months ago. And I also want to mention that Dushyant and Ray Harrison will be giving a talk tomorrow on Hadoop security. And I have some other Comcast folks that are giving a talk right after this one in the next hour. Dave and Emron from the customer experience team, they're talking about self-service ingest with NiFi and Kafka. And if you missed Barbara Ekman's talk yesterday on data governance with Avro and Atlas, I recommend checking it out. As we get started here and people get sitting down, can I get a show of hands of who uses Dr. Elephant? Anyone? Okay, it's a few of you. Happy to announce that Ravant on our engineering team has just finished committing the final bits, adding TES support to that engine, and expect to see an announcement in the coming weeks from that team on that development. And so to get us kicked off on this Smackdown, I'm going to turn it over to Dushyant.
Thanks, Mike. Good morning, everyone. I'm Dushyant. I'm an architect in the big data team at Comcast. To start off, I'll give a background of our environment at Comcast. So our enterprise data lake has got 1,000+ daily active users. We do have about 70 racks and petabytes of usable enterprise data available through the Hive. Our environment is 24/7. And our use cases range from ad hoc jobs, batch, streaming data, and reporting. And we do have like n number of third-party tools and reporting tools that are being used on the cluster data. Some of the use cases we have depends on the speed of the SQL engines that we use. Some of the business reports and the decisions that are being made depends on the data that's coming out of the cluster daily. So it's important for us to pick a SQL engine which would give us the best performance for the interactive queries. So the tests were run against the SQL engines MapReduce, Spark, LLAP, TES, and open source Presto. All the tests were run independently, and the end goal was to pick a SQL engine which we can recommend to the C-suite and also for the general user community. So the test was set up on physical servers with 11 masters, 32 cores, 90 gig of RAM, and a top rack switch of 40 gig. The latest versions of HDP 2.6 were used, and we used the open source version of Presto .175. So all the test data and the queries have been taken from the Hortonworks benchmark repository. We have taken the initial data set of 1 terabyte from the repository, using which we build like rest of the test data sets for running the tests. So these are the data sets that were generated, Parquet, sequence, and text using different storage formats, bzip, snappy, and zlib. A total of 66 queries were run for each of the SQL engines. Each of the SQL engine was run one at a time, and it has been tuned to take the complete resources of the cluster. The queries were run, each of the query was run 3 times to make sure there were no anomalies. And the average runtime was taken for all the 3 rounds. One other thing was like the open source Presto did not support Beeline. So we have written a simple SQL client to have Presto queries run through Beeline. So all the queries were run using the shell commands, and the time was taken off of the servers. A penalty of 10 minutes was assigned to each of the failed queries. So these are the 66 queries that has been run. This has been like taken out of the benchmark repository. So Mike would be back to discuss about the results to see which of the SQL engines gave us the best performance from the test data sets that we have ran. Mike.
Thanks, Dushyant. And before I go over the results, can I see a show of hands of who today has to support interactive query in their environment? Wow. And can I see a show of hands of who thinks they need to support it in the next 6 to 9 months? Okay, you're all in the right place, and hopefully these results are going to be actionable and help you guide yourself on that journey of supporting interactive queries. And we build this talk as a Smackdown, but there's no folding chairs that we're going to throw. There's no, spandex. There's no wrestlers. Just the good old scientific method of test, observe, and measure. And so that's how we came up with these results. But in running all these queries against the engines, this is a new benchmark, and there are failures across all the engines. And so for a query that failed, we automatically gave it a 10-minute runtime. And so the worst being MapReduce, 8 failures for 80 minutes. That actually kind of surprised us because that's one of the most oldest and mature ways of running SQL in your environment. LLAP had 1 query fail for a reducer error, and that was 10 minutes. Spark, 2 queries. Query 70 was a join operation that wasn't supported, and query 72 was out of memory exception in our environment for 20 minutes. Presto was the second worst as far as query failures. Most of these query failures are just due to there are some date operations that Presto currently doesn't support in the open source version. And they also do not support semi-joins, which a number of queries make use of. The final was TES for 20 minutes, and those were vectorization exceptions. And the first engine we actually looked at was MapReduce. And MapReduce was the worst performing of the engines. It was so bad that we called it a dumpster fire. It took 36 hours just to run one ORC schema through it. So to put that in context, 3 runs of all the queries, that means 12 hours to run the set of 66 queries. This is definitely not a performant environment that you're going to look for as far as a query engine. And to add to that, if we actually had marked all the queries as failed and given them the 10-minute penalty, this would have completed 3 hours faster. Okay, now we get to the bar charts and eye charts. So the first eye chart. So you might be able to see, if you have a magnifying glass, your favorite TES settings. These TES settings come out of the Hive benchmark that's checked into GitHub. They've been optimized for the TPC queries, so we really didn't have to really touch these at all, except for the TES container size up there. We defaulted in our test lab environment a 3 gig container for running all those queries. And so now if we go look at the results across all those data sets, there's an interesting pattern that we all expect. ORC zlib, of course, has been optimized to support TES, and it's in the front, looking at about just over 6,300 seconds. Then followed by the Parquet format, which is 13% slower. And then we get into the non-columnar formats, 21.9%. And then surprising text bzip at the very end, which is 103% slower than running ORC. The other thing to notice is in the middle there, when we're in the non-columnar, gzip seems to be the more optimal performance compression format. And so when we look at the next engine, Presto, here's the settings that we use for Presto. It's pretty simple. There's 4 settings you set in your config properties, for max memory and max memory per node. And then you set your JVM heap size. The goal was to give as much to these operating environments as we had available in our smaller test cluster. And if we look at the results of Presto across the board, there's another interesting pattern that's showing up. The optimizations for Presto between ORC and Parquet are a little tighter coupled, and that there's only a 5% difference when you leave ORC and get a Parquet. Now, when we go to the non-columnar formats, initially these results are faster up to about text snappy. And then there's really no optimizations in Presto because performance starts to drop off and it's even worse. We're seeing, the runtimes between sequence bzip and text bzip are roughly about twice of what they were for TES, with, a total delta of 281% between ORC and going to bzip. And also, if you notice in the middle of the graph, that snappy seems to be the more optimized format for your non-columnar data, which we thought was kind of interesting. So now we get into the controversy. So we also ran all the queries against Spark SQL using the Spark Thrift server. The Spark Thrift server in our environment proved to be very inconsistent. And we actually had a lot of challenges with long GC pauses. These were not little pauses, these were long pauses. And we were getting runtimes for some of the queries that could be within an hour delta. And so getting retrievable results with STS proved to be very problematic, and the only way we could do this is we'd have to start cherry picking some of the results, and so we were forced to scratch that. Now, this is not a knock on Spark SQL. Spark SQL is a great technology. Everyone uses it in production environments, and it's awesome. The challenge is Thrift server is kind of a new technology. They're still under construction. There's still work to be done on that, so stay tuned on developments for that. The next engine we looked at was LLAP. This is a new engine that's supported through HTTP 2.5, and it's easily configured through Mbari. One thing to note, when you're running in Mbari, the settings out of the box are not optimized, and you will actually get worse results with than TES with this engine. And so what we did in our environment is we've given the entire yarn memory heap per node, to a daemon, and we split that heap between cache and processing heap at a 70-30 ratio. That seemed to give us the best performance in our test environment when we were running. And enabling vectorization seems to help take advantage of some of the new capabilities in the execution engine as part of LLAP. It's definitely a different beast than the other engines that are coming standard with the Hadoop. The last couple settings there are more around some fine-tune optimizations that we did in our environment to tease out a little more performance. And so when we look at LLAP, we see a similar trend, but the thing to notice is all the execution times are much faster than the other two engines. And the way LLAP had been billed to me and maybe to a lot of you is this engine is totally optimized for ORC and only ORC. But what we found in our testing is that we achieved better performance across the board, even in the slight improvement in the sequence and text bzip, which was very interesting. But you can see that there's a lot of optimizations in ORC, and then you start dropping off considerably using the other formats, but there's still benefits of running this engine even if you don't have your data in ORC zlib format. So if we dig down a little deeper and we look at the fastest execution across the engines, LLAP was the fastest at 7-8 minutes, and this is ORC zlib. And ORC zlib was the fastest format for the other two as well, with Presto turning in a time of 103.6 minutes and TES at 105.21. Now, these times include the penalty times that we had charged for those failed queries. So that's something to be aware of. But LLAP is clearly out in front as far as those other engines. And then if we actually look at which queries were run the fastest by each engine, in our environment, LLAP ran, of the 66 query, ran 44 fastest of all the engines. Presto with a distant second of 16, and TES was actually able to run 6 of the queries in the environment faster than the other engines, was a little bit of a surprise to us. So if we actually look at those top two engines and we plot them across the queries, notice at the 600 mark, there's a red line going across. That's the failure line. So you see every query that's touching that line, that was a failure in execution. And you can see that LLP has, one query failure at 29, but it actually at query 67 exceeded the failure threshold in running that query. It was that one anomaly. And you can see the failures for Presto at the 70-second mark and above up to the 95, 96. Now, the thing that's harder to see on this graph is that most of these queries are actually executing well sub 100 seconds, and even, for the most part, sub 50 seconds. We're definitely in the realm of interactive query across both, except for the outliers toward the end. And these queries that we're running for TPC-DS, they're not designed to be interactive. They're designed to stress your system. So, these results are a little telling that, they both seem to be really, really fast engines with LLP, having a slight lead. And so, some of the other observations I want to pass along from us running these tests is that there's really not a good way to tune these engines without trial and error. It's still an art. There is no science. There's nothing to tell me that all the gains that you can achieve are gotten. I'm sure that a bunch of you can come up after this talk and say, if you did these 5 things, you would have increased your performance by X percentage. The other thing that was really interesting was when we ran these engines, our environment was not memory rich. We're averaging about 3.5 gig per container, or I'm sorry, per core. And if you're running Spark or you're running LLP or you're running Presto, they want as much memory as you can give them, and giving them 3.5 gig is not very generous. But they actually executed pretty well, and they outperformed the engines that aren't memory memory intensive. The other thing that we found is running LLP and Presto in our test environment, it was rock solid. No issues, no restarts, no hiccups. Definitely very solid engines, and they're ready for, I think they're ready for production use. And additionally, they also played well, all the engines played well in the Hadoop environment. So adding, one of these execution engines into your environment should be very straightforward, and you're not going through and reconfiguring a bunch of your services to make room, and so it would play nicely. They all played really nicely, and things really, really worked well. I told that we'd talk about winners and losers, and so first our loser is MapReduce SQL workloads. If you still have jobs that are running in MapReduce SQL engine, I recommend you stop. It's wasting resources and time, and there's a lot of better choices that you can utilize in your environment readily. The other loser that surprised us was bzip compressed text and sequence files. It has been a common practice to take your source data and just land it into Hadoop and just compress the crap out of it with bzip. But if you're actually going to query that data on a regular basis, the performance penalties is worth revisiting that decision. And finally, it's the Spark Thrift server. We hope this is a temporary situation that gets resolved, because that's a good technology and more choices are better. But right now, it does need some work. The winners, so for the C-suite, hands down, it's LLAP. It executed the queries the fastest, and it had the most wins on query execution. A runner-up is Presto. If you don't have to worry about a lot of date casting and semi-joins, it's a really good engine too. You won't get as good as performance with LLP, but it's a good second choice. The other thing that was really surprising was ORC zlib is the compression format across all these engines that gave the best performance. When we compare it to the other columnar format, Parquet, there was really no clear winner. Each engine did better on different formats, so there wasn't really, a clear optimization that favored one compression format over the other. But this does talk to the fact that, when we're getting into interactive query performance, the columnar formats are where the future is. And that's where the focus is going to be for the optimizations. It's easier for the engineering teams to start adding, Bloom filters and the push down predicates and the index ordering on these columnar formats than it is on the legacy, text and sequence. And so with that, we're done, and our team in Colorado is hiring. If you're looking for a fun place to work, any questions? Okay, is there a microphone, or if you can speak loud? Sure.
Hi, I'm curious as to how you selected the competitive set here to test. Obviously that's not the complete universe.
It is not the complete
Right.
universe.
So obviously there are different analytical applications that your users have employed, right? And I'm on the business side, by the
Sure.
way, I run an analytics team. So different tools have different characteristics in terms of how they work with the SQL engine. So basically the question is, how did you select the set? And think about that in the context of the user tools.
Sure. And the set that we did start with was mostly geared around the most popular engines available. There was no consideration about particular analytics. And since we're running the synthetic TPC queries against those data sets, it really didn't advantage any of the tools. And so, the original goal that we had set out was, if I need to support, interactive query to non-Hadoop users through traditional BI tools, this was the set that, readily came to mind that we could do our tests with. Definitely is not complete, and we would love to have tested more tools, but this undertaking just with these tools, it took 3 months to run all those queries twice and to verify the results. It's a tedious undertaking.
One more quick question associated with that. If you could have tested more tools, what might those have been?
That's a really good question. We initially had Drill on the list, but Drill actually uses a lot of the underlying engines. I'm not recalling some of the other choices. Yeah. Yes?
Can you speak to the issues around the Spark Thrift server? Was it a memory issue, a Spark level suspected bug?
So it seems to me that from what we observed, and I'm not going to say we know this for a fact, but what we observed was that running the Thrift server, there was a lot of, since it's embedded the Hive server too, there was a lot of object creation in the from the analyzing the query plan and to execute it, that it seemed like the pauses were consistent with doing the plan analyzed, and that's where we've seen the GC pauses. So yeah, it definitely didn't seem like it was with the Spark execution. It seemed like analyzing the query, and that's where we're seeing the pauses. Yes?
Was there a difference in the amount of memory given to LLAP and Presto, or was it identical?
I won't say that they had the exact same number of bytes, but the goal was to give them as much of the system resources as possible. And from talking with our engineering team, that was the memory recommendations they had given us. We wanted to present these results so that you could look at them and try to replicate it and say, oh no, you guys are off. You should have set these settings, and you would have been better results. Yes, in the back right there. You, yes.
Did you consider running the full TPC DS benchmark?
We did. The issue is that the entire TPC benchmark is not supported by all the engines as far as I know. And so we worked with the known set, the known universe of working ones, and then use that as the basis. I understand that TES LLAP does support more of the universe, but we didn't really have a whole lot of time to investigate the remaining 30 some queries to see if they would work in that environment. We thought we got a pretty good representative of the original 66.
So would it be fair to say that the 10-minute penalty distribution would have been different across sections?
Yes, it's fair to say yes. If we ran them all, then yeah, it would have been. And our thought was if we tried to run them all, that 10-minute penalty would start skewing the actual test runs. Yes. Yes, you. Yes.
Sorry, probably I missed the part. So my question is, how big is the test cluster? How many machines in there?
So the test cluster was 11 data nodes and 5 masters. With each, the masters had 90 gig, 32 core machines, and the data nodes were 128 gig machines with 32 cores. And there's 12 drives hanging on each of the data nodes.
So the test data size is how many terabytes?
It was 1 terabyte. It generated 1 terabyte TPCDS. Yeah. Yes, green shirt.
Did you configure the multi-tenancy on this cluster?
No, we did not. No, we did not configure for multi-tenancy. Since we were running individual tests serially, we didn't bother doing that. So, but that's a really good point that these test results might look a little differently if you start running multiple queries at the same time in parallel. Yes. Yes, sir.
So what is the SQL engine is currently in use in the production environment, and how is the business response to it? Like, are we satisfied with that?
So currently we are using our in production environment, we haven't upgraded to HTTP 2.6. Our production environment is still 2.4.3, and in 2.4.3 we're still running TES, we're running a little bit of Presto. We haven't been able to take advantage of LLAP. I would say the business users, they're still used to the interactive speeds they get with their Oracle systems that we're trying to replace, but expectations have to be adjusted because we're getting closer to interactive, but they're still not sub-second like they were getting on their traditional relational database system.
And right now Presto has been like a lot of help for us, but Presto has got some restrictions with like the authentication and like everybody can run like everything. So we are kind of like restricting the use of Presto too.
Yeah.
But if you're still on the older versions, like Presto is a very helpful tool.
Yes, sir, in a blue shirt.
Was there any variances from the first time you ran some of these to the next time, like big gaps or anything, or cache out or anything like that?
So we did see that, and we saw that mostly on the LLAP engine, and we saw that consecutive runs would get a couple seconds faster if it's able to use the cache. If we were totally out of cache, the runs would get a little slower. The Presto engine was more consistent, same runs across all 3, so it didn't look like it was taking advantage of caching. When we ran the Spark engine, we did see variance, but we couldn't tell if that variance was due to, maybe some micro garbage collections. But there was definitely a little bit of variance with LLP on the plus side of running concurrent queries. Yes, sir. Blue shirt. So the question is, do we have Kerberos enabled and we run this on a previous version of HTTP? The answer is we did not have Kerberos enabled, and we did run this on the 2.6 environment. We ran them all in the same environment. It was just turning off one engine and turning on another and running the same tests against the same data set. Yes. Yeah, there is. Yes. Any other questions? Okay, yes, sir. Yes.
So you were showing before that LLAP was faster for running the majority of the queries, but Thrift and Presto were able to run faster for a handful of queries.
Correct.
What queries did Tez and Presto perform better at than LLAP?
Off the top of my head, I can't tell you, but if you see me afterwards, I can show you the spreadsheet and we can look at those queries. And if there's no more question, I appreciate your time and your attention for this.